We have a number of people MIA right now. For whatever reason, this section more than the previous one. So, alrighty, well, welcome everybody to Fluids. For those of you, did anybody get a chance to draw fun icebergs and see which way they float? It was gripping, right? And they turn super slowly. I don't know. So if you got my email from earlier, I don't know. I saw that when I was scrolling through Twitter this weekend, and I thought of you all. It's like, this is just what you need as a fun game to play. But it is, I don't know. I thought it's kind of interesting that the way that you always, if you Google like iceberg, there are tons of pictures of icebergs, and exactly 0 of them are actual stable orientations. They always draw them as like, here's the water, and we draw icebergs like this. Like, it's not going to float upright like that. It'll tip on its side. But we always, every single picture you draw, or every single picture you see, that's how we always draw icebergs as floating, which is silly. Anyway, but and one of the video that I sent along in that email is actually, it would be wild to watch it. So as icebergs melt, their center of mass can change, which changes the center of gravity, and like they can become unstable as they're melting. So you can see this whole ginormous iceberg will just flip as it starts to become unstable, which just would be a really cool thing to actually watch in real life. So there's a video of some people in a boat that are entirely too near to this like really, really big iceberg that's flipping over. Anyway, hopefully have a little bit of fun with that. Draw some icebergs. Now you can, kind of scoff your head, and, when you see people show up an image of 90% of an iceberg is underwater, you go, but it wouldn't sit like that. It'd be on its side. And you can be knowing and, look down on people that don't know as much as you. That's what we do, right? The beauty of becoming an engineer. You know that things are wrong when others don't. Okay, so it's been a little while since we did fluids stuff because we had the exam on Friday. But what we have been doing is starting to try to look at how we can apply physical laws to moving fluids. It's not super straightforward because we're used to applying physical laws to like, here's a ball and I push it with a force, and force equals mass times acceleration. Right, we could do that. We can draw free body diagrams, and we can do force balances on things. But when you're like, how do I do a force balance on this fluid that I push it and it oozes and goes everywhere? Like the physical laws still work, but it's different in how we actually approach it. So like I said, this is the math that we're going to be doing. It's going to feel overly complicated, and in some senses it is. And we're going to eventually get to like, okay, here are ways that we can skip steps and do things easier. But before we get to that, I want to show you at least how we can do it step by step and kind of go through the math, see how it all works out. We'll do that specifically with conservation of mass, because conservation of mass is the easiest. It's always good to start small and do the more complicated things with the easiest problem, because that stays relatively easy, even if it gets a little ugly. And then we'll see, okay, how can we take this same framework or the same idea and apply it to cooler physical laws like F equals ma, and start to see how do fluids move? Like when you have a jet engine that's blowing air out one way, how come the jet goes the other way? Or when you have a fire hose and you turn the water on, how come it like pushes back against you? Those are all F equals ma type questions, but we could figure out like, what are the actual forces involved? So that's kind of where we're headed. We won't get there today. We'll get to maybe the start of talking about what are some of these other physical laws and how can we apply them. So today we're going to focus on just conservation of mass, because it's the easiest physical law, because mass is conserved. You don't have to deal with like forces and accelerations and things like that. You just say mass doesn't change. So we'll do this in the context of, we're going to go through kind of all of the math in detail through the context of this example problem, an example problem. And then, like I said, eventually we'll show how we can do the same thing, but easier without as much work. But we'll do it kind of in all of its glorious detail today. So let's think of an example problem. Okay, so what we're going to have is a wall that a pipe is coming off of the wall. So here is the opening for our pipe. It extends this way for some length. I don't know. And the diameter doesn't change. So this is a constant diameter, just a pipe. Pipe extending from a wall. What's going to happen, we're going to look at a section of this pipe. We'll look at this section. I'll draw it kind of in blue. Let me not draw it that. Leave yourself a little room at the end. So this is our control volume. Okay, so we have two sides of our control volume. We have one side here, we'll call side 1. We have another side here, which we'll call side 2. Or control surface 1 and control surface 2, right? Where the control surfaces, those are the places that stuff can actually go in and go out. So we want to look at how fluid is going into our control volume and how fluid is going out. And we're going to say that has to obey conservation of mass, because everything has to obey conservation of mass. Except stars, but they kind of do still. Right? Nuclear reactors, stars don't totally obey just conservation of mass. But conservation of mass and energy. Anyway, this is not a star. This is a pipe. So we have fluid coming into one side. So what does that look like? Well, it's going to be coming in, and actually it would be relatively flat for the velocity profile. So the velocity is going to be flat like that, where it's going to have some speed. We'll call that speed u. Okay, it's coming in, it's the same speed everywhere. Somewhere down into the pipe at where it comes out at side 2, the velocity profile is no longer going to be flat because we've had friction effect, right? Friction with the wall. It can't be flat because of the no slip condition, right? It has to be stopped at the walls. So it's going to be stopped at the walls, fastest at the center. We don't yet know how to figure out what exactly it would look like. Eventually we'll be able to, and you'll be able to like derive it pretty easily for yourself. But it's going to be stopped at the walls, fastest in the middle, and it's going to look something like this. Okay, where this distance here is, we'll call that U max. Right, the maximum speed there. If we looked at the equation for the velocity at each of these points, we could write the equation for the velocity here would be simply the speed, and we would give it a direction, I hat. I haven't given axes on my thing yet, but this would be the radius, and we'll let the x dimension be down the length of the pipe. So we'll put these axes on our thing. So it's going to be, what's the velocity? Well, it's the speed, and it's the same everywhere, and it's pointing in the x direction. 2 is going to be a little bit trickier. Like I said, we don't know what this equation is yet, other than me just making it up here out of thin air. We'll figure out how we could derive this later, but you've seen this before. This would be U max, our maximum speed, 1 minus r squared over capital R squared. Again, in the x direction I have. Okay, so these are the two equations for our velocity. We know intuitively, like, they have to be related to each other because the stuff going in has to come out. So we're going to go through the math of how exactly that works and hopefully be able to find how they're related to each other. Right, so if we know the speed going in, what is the maximum speed somewhere down the pipe like this? How these two things have to be related to each other. So we're going to do that by applying conservation of mass. On our control volume. What that equation would look like is this. Rho d v, so velocity dot d a. So we talked about this equation briefly Wednesday and Monday a little bit. Mainly on Wednesday, we talked kind of briefly about this and said, actually, this is right the same kind of thing that this is saying that the mass flow rate in equals the mass flow rate out plus accumulation. So this is the, right, how does mass change for a system with time? It doesn't. This is accumulation, right? Are we accumulating mass inside of this section of our pipe? And this is mass in and out. Right, mass flow in, mass flow out. It's the net flow out of the pipe. So if we have two things, one, if we have, or let me call it A, not to get, so A constant density, and B steady state flow. So we're going to use these two things a lot, pretty much all the time. Because if we start to have things that are changing with time, things get messy really fast. And if we start to have things that are not constant density, things get messy really fast. Most things, liquids, I think it's pretty easy to see, like liquids typically are constant density. The density doesn't really change that much. Gases, right, density and volume and pressure and like those, temperature, PV equals nRT. Density is not always constant because gases are squishy. But in fluids, in like fluid flow, gases actually are usually about approximately-ish constant density. Where they start to stop being constant density is when you start to approach the speed of sound. So speed of sound things are weird and behave weirdly. So if you ever like want to look at why it was hard to break the sound barrier with a jet, because the sound barrier is kind of a weird thing and fluids start to behave weird and you have to do weird things to break the sound barrier that you don't have to do if you don't break the sound barrier. Like it is. So that's like a real barrier that things behave different when you get there. Anyway, some kind of counterintuitive stuff. I'm not sure if we'll get to that at all this semester or not. It will be fun if we can. But I'm not sure if we will. So mostly we'll be doing constant density, steady state, simplify our lives greatly, and we'll maybe look a little bit at what happens when that's not the case. But mostly this is where we'll live. Okay, so constant density, steady state. So steady state this whole part of the equation is equal to 0 if it's steady state. That's the accumulation term. So steady state systems, there's not an accumulation because it's just in and out. Like what goes in must come out. So we're going to typically write that, and I'll force you guys to write that part of the equation, but then we're going to cross it out. So it will make our lives easier. So then we have 0 equals the integral over our control surface of rho v dot dA. Okay, and it's a relatively simple equation, but it's kind of a weird looking one. So we have to figure out how do we actually use this and apply it to our actual example. So that's what we're going to work on for the next, I don't know, we'll see, 15, 20 minutes. Okay, so what are our control surfaces? So our control surfaces, we have 2 of them. It's where stuff is crossing a boundary. So one is right here. So that's our first control surface. Our second control surface is right this side right there. Those are our 2 control surfaces. So we can split it up and look at like each of these individually. So this we can split up and look at our control surface 1 of rho v1 dA1. As you're writing this in your notes, make sure V and A are both vectors, and make sure you put a dot in between them. Because they are vectors, we are taking the dot product of those vectors. It will help us to keep track of signs and do all the math and vector notation stuff right. Plus the integral surface 2 of rho v2 dot dA2. Okay. So we have these 2 surfaces, and we're trying to take, right, I mean, maybe this makes sense. This is mass flow rate. So the mass flow rate is density times velocity times area. That's what we're trying to do. We're just doing it in the calculus version of that. Okay, so what are the bounds on our integration? We're trying to integrate over the whole area, and we're trying to integrate over a differential area, dA. So what exactly do we mean by that? Well, we're trying to go from right that whole circular area, but in a coordinate system that we can actually like do integrations and stuff with. So the our differential area, get my black. So our differential area dA, what exactly is that? So our total area is a circle. So a differential slice of that circle is going to be so it's going to be a donut shape where, I'll zoom in. So this dimension here is R, and the thickness is dr. I drew it sideways. Right, I guess maybe I should write it like this. Draw it sideways and then write just a circle like this. Circle like this. So this is R. It's a really thin donut with radius R and a thickness dr. Why I wrote it sideways, the direction And this is how we're going to keep track of sign convention stuff. So the direction is the outward normal. So it's pointing out from our surface, out away from the center of our control volume. So what would the area be of this guy? So this would be dA. Okay, what is the area of that little donut slice? It's going to be the total thing. Well, we'll write dA without the vector. This is equal to the total area, so R 2, or sorry, not 2, pi R plus dr squared. That's the total outside area, minus the whole, minus pi R squared, right? So the total outside minus the hole in the middle. If we actually did the multiplication of that first thing, this would be dA, well, so this is pi R squared minus 2 pi R dr plus, plus 2 pi R, I don't know why I had a minus, plus pi dr squared minus pi R squared. So those two will cancel each other out. dr is really small by definition. So dr squared is really, really, really small. Because you take a really small thing that's infinitesimally small and you squared it. So you made it even more infinitesimally small. So our differential area, dA, equals 2 pi R dr. Okay, so for this geometry, so then what defines it, we have to look at from our bounds of integration, we're going to look at from the center of our thing, where that radius is 0, that'd be the center dot, all the way to the exterior radius, capital R. So our integrals now become 0 equals the integral from 0 to capital R of rho V1. No, this is 2 pi R dr. Let me write it like this. Let me write a bracket. And then which direction is that pointing? Well, how I've drawn it up, this would be pointing in that direction, the negative x direction. This one's going to be pointing, again, outward normal, so that'll be pointing in the positive x direction here. So this is in the negative I hat plus the integral from 0 to R rho V2 of 2 pi R dr I hat. And again, we should have a dot product between the V and the differential area. Okay, so this gets us a little bit closer. Now we're integrating with respect to R. We have to plug in what those vectors V, what the velocity vector is, an equation for that with respect to the radius, because that's what we're integrating. We're integrating with respect to the radius. So now we can plug in V as a function of R. And we get from 0 to big R of rho. This is U I hat dot negative 2 pi I hat dotted with 2 pi r dr I hat. Okay, so I told you this was going to get a little bit ugly, and it does. We can do the next part is the dot product. So the dot product is super easy. So for this, right, I hat dotted with I hat equals 1. So, okay, it makes it easy. If they weren't lined up perfectly, that wouldn't necessarily be 1. But if they're both lined up in the same direction, that equals 1. We got a negative sign in here, right? This negative sign came in because of the area was pointing in one direction and the velocity was pointing in the other. So we'll make sure to keep that, but that equals 1. And then we can pull out constants. Okay, so let's pull out constants. So in that first term, what are constants? We have negative 2 pi rho capital U are constants, and then we're left with r dr. Plus, pull out all the constants we can from this other one. We have 2 pi rho U max of r 1 minus r squared over big R squared dr. Okay, I think I did that all correctly. Cool. So now we have 2 different integrals that we can actually do the integration on relatively easily. So let's go and do that. So this first integral, this equals minus 2 pi rho what is the integral of r dr? The integral of r with respect to r is r squared over 2. So this is r squared over 2 evaluated from 0 to capital R, which is equal to minus 2 pi rho u. So it's going to be capital R squared over 2 minus 0. So the 2's will cancel each other out, and this will be equal to pi r squared rho u minus pi r squared. Minus pi r squared rho u. All right, you could have told me that without going through all the integration, right? So what is the mass flow rate into the left-hand side? We did this on that one like in class thing. So it's the velocity times the area times the density. So the velocity is u, the area is pi r squared, the density is rho. Right, so this is just velocity times density times area. So that one was kind of easy, but it's nice to know, like, okay, we went through all of the math and actually did integrations and we got the exact same thing. The one where we actually like needed that whole process, what is this second one? So for the second one, it's not clear exactly how, without doing the integration, at least it's not to me, how the mass flow rate is related to this max velocity, because we now have like a parabola shape. So this one we actually need to go through our integration. So this is Well, I'll write it like this before we do the integration so that it's a little bit easier. Rho U max. We're integrating from the center of the pipe to the pipe walls of R minus R cubed over capital R squared dr. And this, I write it like this so that then we can do the integration in two different parts. So this is going to be equal to 2 pi rho U max. Okay, so the first part is the integral of R dr. So that's R squared over 2. So R squared over 2. Well, let me just, okay, minus R cubed over R squared. So that's going to be R to the 4th over 4 R squared. So R to the 4th over 4 R squared. And we're evaluating this, our bounds of integration are 0 to R. So that equals 2 pi rho U max big R squared over 2 minus, so we have big R to the 4th over R squared, so that's R squared over 4. Okay. Again, if we simplify this out a little bit further, the 2 will cancel out the 2 on the bottom, and then it'll half cancel out the 4 on the bottom. So this will be rho U max pi R squared times 1 minus 1/2, or rho U max pi R squared 1/2. Okay, so we have these two, this and this, both from our equation up here. So let's plug both of those in. So we'll put all this stuff together. So minus pi R squared rho U, so 0 equals minus pi R squared U plus the pi R squared rho U max over 2. We could write U equals U max over 2. Right, our pi's and our r's and our rho's all will cancel out, and we'll just get this simple equation. So the velocity at the inlet, which is this flat velocity profile, is related to the parabolic velocity profile. That maximum speed is twice what the inlet speed is. But obviously, it's kind of a journey to get to that relatively simple. But maybe you can see with this how we would get a little bit, at least, how we can use this type of a framework to really, in detail, track what's coming in, what's going out. We do it in vector notation so that we don't have to really worry about sign conventions, like the sign convention for whether something's coming in or whether something's going out. The sign conventions will take care of themselves as long as you get the vector notation right, like are the two dot products, is it two vectors pointing in the same direction, or are they pointing in different directions? Exactly how that specifically works. And we get, the velocity U max on the right side, that's twice what the velocity at the inlet was. And that has to be the case because that is what would satisfy conservation of max. Yeah, perfect.
Why are the green arrows both defined outwards?
Always are outwards. So the areas are always going to be an outward normal. So when we're looking at the area in vector, so we're doing like these guys in vector notation. These are both always going to be outward normal. So they're always going to be pointing out of the control volume, never like one out and one in. And that's just a convention. Like you could always have them pointing into the control volume and things would work out just the same, but we just say we'll always point them outward. Okay, so we will spend some time as we start to get into more problem solving with this. We'll spend some time kind of detailing what ways we can make our lives easier and not have to go through all of this process for every single problem. But in some problems, we will have to go through the whole process to be able to look at not just mass flow, but the flow of like momentum. So that's what we're going to be doing next, is trying to take this same framework and apply it to other types of physical laws. Right, and I guess the framework that I'm talking about, right, is we're used to applying physical laws to a specific amount of stuff. Like we have this ball, and I apply a force to the ball, and that's going to give it an acceleration in this direction. And I can figure out F equals ma, and I can do a free body diagram. What are the forces acting on the ball? And that's going to tell me how it's moving. It's weirder and harder when you're doing it on a fluid, because fluids, right? You can't like define this specific little chunk of fluid and then you push it and it goes all over the place and spills on the ground, and you're like, how did this all happen? So we're going to figure out how do you take some of these same types of physical laws. We'll spend most of our time with F equals ma. We'll do other ones too a little bit, but we'll spend most of our time with F equals ma because a lot of times, right, if you're trying to look at how fluids flow and move, they respond to forces. They respond to forces by F equals ma. So that's where we're going to be spending most of our time. But the end of today, I just want to show you a little bit how we can start to generalize these same ideas to some of these other types of physical laws. And then next time we'll do some problem solving and simplify stuff. So we'll spend quite a bit more time on that next time. So the framework that we're going to look at is, we have like a change in some property with time. So how does some property change with time for a system? And by a system, like a well-defined mass, how does that change with time? That equals the accumulation inside RCD plus the amount so this is the framework that we're going to use. We can do this for a lot of different types of laws. So if we have a basic law, right, so the rate of change for the system, I guess rate of change of property for a system. So we're going to make a big table. Then we'll have here the extensive quantity, which we'll call capital N. And here the intensive quantity, which we'll call eta. Right, the extensive quantity is the total amount of whatever it is. The intensive quantity is the per mass amount. So the intensive quantity equals, right, so total amount equals mass times the intensive quantity. Okay, so what are some basic laws? So we have conservation of mass. The rate of change of mass for a system. How does mass change for a given mass? Mass is constant. It's not changing. So we would write the change of mass with time equals 0. Our extensive quantity, the thing that we're tracking, is the mass. Mass divided by mass is, this is kind of a goofy one. So mass divided by mass is 1. Right, mass over mass equals 1. Another law, Newton's second. So Newton's second law, we typically would talk about this as force equals mass times acceleration. F equals ma. And we could write that as like vectors. We're going to formulate all of these in terms of like the change in something per time. So instead of mass and acceleration, acceleration is a change in velocity with time. But mass times acceleration, that's a change in velocity times mass per time. So that's a change in velocity times mass is momentum. So we'll write this as dp dt equals f. So how does momentum change with time? That equals force. Our extensive quantity is P. Our intensive quantity then is momentum divided by mass, which is the velocity. And right, we can write P equals mass times velocity. We have a lot of P's and V's. Those are popular variables in fluids. So P is momentum, V is velocity, not pressure and volume, but momentum and velocity. That's why it's nice to do vectors, because you know pressure is not a vector, so it must be momentum. So Newton's second, conservation of mass. These are the two that we'll do most often. But we can take this same framework and apply it to other stuff. So we could do angular momentum. Right, which is just kind of a riff on F equals ma. For the principle of angular momentum, we could write that the dh dt equals the torque. right where H is the angular momentum and T is the torque. We would write then the extensive quantity is the angular momentum. The intensive quantity is R cross V. R cross V, because H equals R cross M V. We won't do too much with that. We could do this with the first law of thermo. Right, the first law of thermo, we have typically thought about this in the context of thermal class as like the change in internal energy plus the change in kinetic energy plus the change in potential energy equals heat minus work. Right, remember you wrote that lots of times. So, okay, the change in internal energy, the change in kinetic energy, the change in potential energy, that's the change in the energy of the fluid equals heat minus work. So we can write this, the first law, as the change in energy with time of the fluid equals Q minus W, where our extensive quantity is the energy of the fluid. The intensive quantity would be the lowercase or the specific energy of the fluid, right, where E equals mass times the energy of the fluid. And we could even do, we won't do anything else with this other than what I'm writing here, but we could even do the second law, where we would have the change in now the entropy with time. And the second law is the weird one because it's not an equality, it's an inequality. So it's greater than or equal to Q dot over temperature. And the extensive quantity would be the total amount of entropy. The intensive quantity would be the specific entropy. So for all of these different physical laws, we're going to cast all of them into this, to this framework, which we'll call Reynolds transport theorem. So all of those things can be cast, and I'll write this down and we'll expand on it later. So we could write that the change in the extensive quantity for a system is going to be equal to the accumulation of that quantity, energy, momentum, angular momentum, whatever it is, of the intensive quantity, rho dV, plus that, how that quantity, again, energy, momentum, entropy, whatever it is, how that's flowing into the system, velocity dA. So this is the framework that we're going to use to be able to track these physical laws for fluids where things are going in and out and potentially having, like we did in that conservation of mass example, like the velocity isn't necessarily going to be constant everywhere. We could have fun things going on. So we'll pick up this next time, start to apply it to F equals MA so we can do some more exciting problems. But come prepared for a little bit more fun calculus stuff on Wednesday. With that, I hope everybody has a good Monday.